really summarizes almost everything. And I hope that you have like different colored highlighters or pencils with you, because I like working with colors when it comes to this map, because it helps you to look at each thing individually and identify the type of reaction that you are working with. So before I actually look at this map with you, I'm going to use the color yellow for addition, to show addition reactions. I'm going to use the color blue to show elimination. I'm going to use the color green for substitution. And then I will use red for either oxidation or reduction. And I will use orange for any reactions associated with carbonyls. So I'm going to zoom into this top part here. And that's how you also study from this thing. You always look at a specific section at a time. Otherwise, it is just too much to handle. So if you start here at the center and you look at what is given, you know that you have an alkene. And the only reactions that we have now learned with alkenes is when you add something to an alkene to turn it from an unsaturated molecule to a saturated molecule. So the only thing that I can think about here is addition reactions. So we're adding to make it saturated. So if we start here, if we start with this arrow here and we are going in that direction, we are adding HX. So this is going to be a hydrohalogenation. It's a hydrohalogenation reaction. Okay, you're adding an X and a hydrogen. So you're adding either a chloride or a bromide, or you can even add an iodide. Okay, hydrohalogenation. When we are moving in this direction and we're adding chlorine or bromine, then this is just normal halogenation. And remember what we said here with halogenation, this is an anti-addition. So if you look at the stereochemistry, one will be on a wedge and one will be on a dash. That's halogenation. If we look at this reaction here, it even tells you this is a halohydron because you have a halogen and you also have an alcohol in your molecule. So this is halohydron reaction, and this is, as you can see, also anti-addition. Anti-addition. Okay, I hope I'm not going too fast. If we then work from here on alkenes and we go to our alkanes, we're adding hydrogen. This is normal hydrogenation. And we're adding that, and you can clearly see that this is a syn addition because they both add on the same side. Okay, so this can be like that. What is the purpose of this now? Probably just to show that it can go on either side. So it could be like that, or it could be like that. Okay, and then another addition reaction we looked at, remember, was when we looked at this alkyne and we're adding Lindlar catalyst. We can go back to an alkene, or we can add just normal hydrogenation things to make sure that our alkene goes all the way back to a normal alkane. Okay, so that was really everything about addition that you need to know for theme 4 and theme 5. And it's actually funny if you look at this again, and we now look at the elimination reactions, you can actually see from this diagram that the only elimination reactions that you see here is when you go, remember elimination is from saturated to unsaturated. So you're starting with, you can see it's an alkyl halide. We want to eliminate that. But what we are doing here with this OH is a dehydrohalogenation. Dehydrohalogenation. And you end up with your alkene. And the only other elimination reaction that we talked about was when we have an alcohol and we're eliminating the OH group with sulfuric acid, concentrated sulfuric acid, and that is when we do a dehydration. That's the only two elimination reactions on this entire map. Oh, I see that I've missed another addition reaction. If we go down and we add water in that, this is just a normal hydration. That's just a normal hydration reaction. Okay, that's the addition and elimination that you will see in theme 4 and 5. And now if we look at what we have in the second part here, I'm going to start with substitution. So with substitution reactions, if you have a primary alcohol, then you can substitute that with SOCl2 and PbR3 to form an alkyl halide. So you just substitute the alcohol with a halide. So you can do exactly the same for a secondary alcohol. And then lastly, for a tertiary alcohol, you can just add HX. But it's for the same purpose. Tertiary alcohols are more reactive, so you can substitute to form an alkyl halide. And then there's another substitution reaction that is actually not shown on this map. That is if you, I'm just going to add it here. If you have a secondary or you have a tertiary alcohol, and you also want to form an alkyl halide, then there's another reagent, HCl and zinc chloride, and this reagent is known as Lucas reagent. If you see something like that, you also know that you only have a normal substitution reaction. Okay, let's quickly look at the rest of this map. With your tertiary alcohols, let's go to our tertiary alcohol, and I'm going to use the color for carbonyls. But if you now add sodium or potassium, then you just basically, because these act as you can say it acts as a base, so it basically and this then acts as an acid. So this what's the name? So this will deprotonate the alcohol, and when it deprotonates that alcohol, the hydrogen is taken away, and then you just form an alkoxide. Okay, so it's just without the hydrogen. However, please note, and this is extremely important, when you look at tertiary alcohols, and you look at, this is an oxidation reaction, tertiary alcohols does not undergo oxidation. Okay, and for the simple reason why it cannot undergo oxidation is because if you now look at this tertiary alcohol, if this thing were to now oxidize, then you would have to turn that alcohol into a carbonyl. But this carbonyl has 1, 2, 3, 4, 5 bonds, and you know that a carbon can only form 4 bonds, so it's not possible. So tertiary alcohols do not undergo oxidation. However, if you look at secondary and primary alcohols, they actually do undergo oxidation. And they can do that with Jones reagents or PCC. And now Jones reagent, sometimes they might not tell you what, they might not say Jones reagent, but they might say chromium or chromate in sulfuric acid. They can also, because that's basically what Jones reagent is, or PCC. So that will reduce that to a ketone. It will oxidize it to a ketone. This is oxidation. And if we have a primary alcohol and we use PCC, we reduce that to an aldehyde. Why am I saying reducing? Sorry, we are oxidizing that to an aldehyde. Okay, if we look at the reduction side of things, we can always reduce ketones to secondary alcohols with a mild reducing agent. And we can do the same with an aldehyde back to a primary alcohol with a mild reducing agent. If we look at this aldehyde, we can take that and oxidize that. Let me just write here, reduce, and this is oxidize. We can oxidize this aldehyde into a carboxylic acid. And we can also oxidize our primary alcohol to a carboxylic acid. Okay, Jones reagent is a stronger oxidizing agent, so that's why it will directly take your primary alcohol to a carboxylic acid. If you want to get an aldehyde, you need to use PCC because it's a milder oxidizing agent. And then the rest of the reactions are all related to carbonyl chemistry. So if you have a ketone, you can add alcohol. You can add an alcohol with acid to form an acetal. That's what an acetal looks like. And the reverse is known as hydrolysis. If we do hydrolysis, it means that we're just breaking it back up into a ketone. We can do the same with aldehydes. It's the same. We can form acetals. And that's for those. And then if we look at our carboxylic acid, you know that if we add alcohol and sulfuric acid normally, then this is the normal esterification reaction. And if we work from an ester all the way back to a carboxylic acid, that is also hydrolysis. Another name for this reaction, if we go in the reverse, is saponification. And we're going to look at that mechanism as well. And then there's this reaction with amides. Remember, an amide has a carbonyl group. So with amides, if you do hydrolysis of an amide, then it's you can either have acid catalyzed or you can have base catalyzed hydrolysis, and you get back to a carboxylic acid. If it is acid catalyzed, you will go back to a carboxylic acid because in the presence of protons, it will be protonated. But if it is base catalyzed, you will end up just with oxygen minus because it will be deprotonated in the presence of a basic solution. Okay, and that is literally this whole map summarized in 10 minutes.